Dynacam engine has generated tremendous interest in many potential markets. The Dynacam engine is a unique free-piston cam drive engine. It has the same size and shape of a turbine jet engine. It has been FAA certified for both helicopter and aircraft. Its dimensions are 13 inches in diameter and about 39 inches in length. Its main advantages are higher power and torque, higher reliability, 50% less parts, 50% smaller size, better fuel economy, less weight, lower maintenance cost, smooth vibration-free operation, and it is liquid-cooled. With all of these advantages, the Dynacam engine has the potential to successfully compete in any market that uses engine power today. The Dynacam engine can, of course, be built into any size and power required as well, whether it's 1 horsepower or 10,000. The Dynacam engine is a 12-cylinder engine that generates a powerful sound as unique as the engine design itself. Let's take a moment and listen to the Dynacam engine. The engine can idle down to almost 100 RPM. Takeoff speed is 2,000 RPM with a cruise speed of 1,700 to 1,800 RPM. This shows the first Dynacam installation. This one is in a Piper Arrow aircraft. This particular engine was carbureted. Fuel-injected models are also available.
Taking off, there's lift off, gears going up.
Notice the quick takeoff. Takeoff distance was reduced by 40 to 50% from the previous engine used. During flight testing, the engine was shown to increase the performance of the 4-place airplane significantly. Rate of climb was increased from 900 feet per minute to over 1,500 feet per minute. Here we fly in formation with the Dynacam over the hills of Chino Valley, California. Flying in this area requires an engine with high reliability and dependability. The individual component parts that make up the Dynacam engine are extremely simple compared to their conventional engine counterpart, and well designed as a result of 5 generations of engine design changes through research and development. The engine block shows the 6 cylinders that are designed into each casting. Since there are 2 blocks per engine, this gives us a 12-cylinder engine in half the space a normal 6-cylinder engine requires. This is the valve train area that is designed into the top of each engine block. Double-headed pistons like this one actuate back and forth in each cylinder parallel to the power shaft, not perpendicularly to the crank, as in a regular engine. This is one reason for the smoothness of operation found in the Dynacam. This is one of the 2 Dynacam thrust bearings that sit inside the block and ride against the main cam. These bearings absorb the forces produced by the cam due to combustion. The valve cam is also an extremely simple design. This small 2-lobed disc mounts directly on the main shaft and actuates all valves in a true overhead valve arrangement. One lobe is for intake. The other lobe is for exhaust. This small valve cam replaces these parts found in a conventional engine: the cam shaft, rocker arms, push rods, timing gears, timing chain, any balance shaft that is needed, for a fraction of the price and with many less parts. This is the main cam and shaft that replaces the crankshaft in a conventional engine. The same thrust bearing as before is inserted over the shaft and rides against the cam. The valve cam also attaches on the shaft at this location. The main cam or crankshaft and 1 piston are shown on this demonstrator model. This shows the parallel actuation of the pistons with the main cam rolling through the pistons. The pistons have large forged rollers that roll over the cam surface and thus reduce any internal friction to a minimum. It is essentially a roller-bearing engine with 40% less friction horsepower than an equal-powered conventional engine. This is the new aircraft engine. Approximately $4 million in development costs and many years of research and analysis was spent on these 2 engines and the 3 variations between them. This view shows the valve actuation in the Dynacam engine. The engine uses standard automotive-type valves. No sodium-cooled valves are required, since the engine is liquid-cooled. In this view, the roller valve lifters are shown. These roller lifters help reduce any valve train friction to a minimum and virtually eliminate the need for lash adjustment. This view shows how the pistons in the Dynacam engine reciprocate back and forth inside the engine. The pistons move 2 at a time. As one piston fires, the opposite piston is exhausting. Each cylinder fires each RPM, giving 12 firing impulses per revolution. This compares to only 3 firings per RPM in a conventional 6-cylinder engine. Here is a newly assembled engine without the center section. This allows a view of piston actuation with both blocks in place. This one is being turned over by hand, showing the extremely low friction found in the Dynacam design. Try turning a 200 horsepower V8 over by hand sometime, and you'll begin to see how rollers reduce friction in the Dynacam.
Today's market for piston engines is very large. Some 300,000 general aviation aircraft and helicopters are registered in the United States alone. More than 2 million boats in the marine market use V8 or similar engines, and the number grows by about 200,000 each year. And the heavy-duty automotive industry, including trucks, buses, and motorhomes, is very large, 1.5 million engines each year.